to take it a step at a time and see where you guys need help, okay? Hold on, somebody's on the chat. Will you be posting? Yes, I'll be posting the recording on Canvas. Yes. Okay. All right, so let's go ahead and get started. So the first section you guys were introduced to was 5.1, which was called the antiderivative. Okay. And on that section, you were introduced to a couple of things. Number one, you were first introduced to this idea of this symbol right here. This symbol is called an integrand. Okay. And what it means is to basically, if you have an integrand and then you have a function, the integrand always has to have this dx, and that means right here, dx means with respect to x. Whatever variables here needs to match whatever variable you're dealing with on your function for now. That's not true for integrals, but at least for now it needs to match. Later on, once you're more comfortable with the idea of integration, then you can have different variables and then different techniques to analyze that. But you gotta, what you were introduced is that this symbol basically helps you undo a derivative. So the answer of this would be capital F plus C, okay? And this is called the antiderivative. So an antiderivative helps you undo a derivative. That's really what you got introduced to on section 1. Are we okay with that? Okay? You were told that every time you do an antiderivative, you always have a plus C, which is called the constant of integration. Cool? Anything crazy about this? Are we okay so far? Section 1 was just an introduction, guys. Obviously, this is going to get very complex, just like we did with derivatives. Remember, with derivatives, you were first introduced to very basic rules, right? And then after you master those rules, then we went on to the product, the quotient, the chain rule, and then all the other special rules. So that's the same thing you did with antiderivatives. Okay, you have not been really introduced to a lot of integration yet. You just basically were told, like, hey, think of integration, think of your derivatives but backwards. So what I mean by that is, at this point, I think it was, I don't remember, but I think it was Jae-hyun who asked me, like, there was something about a table that was shown in the video. Where is that table at, right? That table's on your textbook, and yes, you need to become familiar with it, but some of these are just common sense. Like, for example, we talked about this. If you have the derivative with respect to u of sine of u, the derivative of that would be cosine of u, right? So if we want to anti-differentiate this, in other words, if we want to go backwards, what you do is you take the integral of this, which is cosine of u, du, and its result should be sine of u plus c. So you've got to basically use common sense. If the derivative of sine is cosine, then the integral of cosine is sine, right? So there's really nothing to teach about that. It's like, do you know your derivatives, but you have to think about it backwards. So let's talk about the same idea. Now, what is the integral of sine? Okay, so let's think about it. What has a derivative of sine? Well, I know that cosine has a derivative of negative sine. So the integral of positive sine would have to be negative cosine. And you can check that real quick, because the derivative of negative cosine would have to be positive sine. And that's how you can check. These are going to be quick integrations that you can check very quickly by deriving them. Okay? At this point, you only know basic stuff. So let's kind of talk about the other one, which was the big one. Okay? The very first rule of derivatives I think I taught you was the power rule. So that's one of the first ones you're going to talk about when it comes to integration. So if you had something like x squared plus 2x plus 1 dx, you have to think of the power rule but backwards. Remember, with derivatives, so let's talk about a derivative. So if you had the derivative with respect to x of 3x squared plus 1, what would you do first to take a derivative? Take the power, multiply by the 3, so that will give you 6, subtract 1 from the power, right? That's the last thing I did, right? Subtract 1 from the power. When you're integrating, you want to reverse engineer that process. So the very first thing you're going to do is add to the power. So you're going to add 1, so that's going to give you an x to the third. And in here you were multiplying, right? Instead of multiplying, you're going to divide by that number that you came up with on the power. So in this case, it's going to be 3. Plus, okay, right now you have a power of 1. If you add 1, that becomes a power of 2. And then you're going to divide by 2 because the power became 2. Yes? And lastly, the constant of 1. 1 is technically the same thing as saying, I'm going to go ahead and here. This is basically saying 1x to the 0. That's the same thing, right? You're going to add 1 to the power, so that's going to be plus 1x to the first power and divide by 1 and plus c. And then you just clean up anything that can be cleaned up. So in this case, it's going to be 1/3 x to the third plus x squared plus x plus c. And you can check that very quickly. The derivative of 1/3 x cubed is going to be 3 times 1/3, which is 1, x squared. So that's going to be x squared. 2x, the derivative of x is just 1. The derivative constant is gone, so I don't have a constant. Are we okay with that? Was there any rule from section 1 that you were struggling with before I move on to section 2? Okay, so then section 1 should just be like, again, I'm not trying to minimize, I'm not saying that this is like a thoughtless process, but you have to basically just think of your derivatives backwards, at least the basic ones, right? Alright, section 2, section 3, and section 6 is really what I wanted to focus mostly on this video, just to make sure that you really understood what happened on those sections. Okay, so I'm not going to label this as anything, I'm just going to label this as area. That's really what you've been dealing with for those sections. Okay, so first I'm going to give you a function. Let's say you have, I don't know, 2x squared plus 3. And then I'm going to give you an interval from 1 to 6. Okay, so I'm not going to go necessarily in order of the way you learn things, but let's just make sure that you understood it. So what I'm basically going to ask you is to find the area between the x-axis, this function, and this interval. Last class, you were introduced to the actual calculus of it. So do you know how to write this as an integral? So this is going to be the integral of what? Hey, Stepan. Okay, 1 to 6 of 2x squared plus 3 dx. Right now, if you know how to solve this because you took AB, amazing. But if you don't, it's okay. We're going to talk about this later on. You at least need to be familiar with the notation. This is basically saying to find the area underneath this curve between 1 and 6, which is what I'm asking you to do. Are we okay with that? Okay. Now, in this video, or at least we're going to review, is how to do this with rectangles with the left, the right, the middle, trapezoids, and then also how to do it with limits. Okay, so let's first figure this out, and let's say we're going to use, just to keep the algebra simple, we're going to use 5 rectangles. Okay, so let's first try the right endpoints. First of all, if we were to graph this, we're not going to do a perfect sketch. We're just going to, again, it's just going to be kind of a sketch. I know I have a quadratic, so it's going to look something like maybe this. Are you okay with that? And what I'm interested on is if this is 1, and let's say that this is 6, right? This goes on forever. I'm interested on figuring out what this area is. Cool? All right. I know that the area of a rectangle, so area of a rectangle is equal to base times height. Cool. So in order for us to do this, if I want to use 5 rectangles, how do I figure out the width or the base? Good. So you do, let me just write this down real quick. You're going to do b minus a divided by n, which is your number of rectangles. In this case, is 6 minus 1 divided by 5. So it's just going to be a width of 1. Are we okay with that? So what that means is that you're going to go here, and then after 1, you're going to go, that's 2, that's 3, that's 4, that's 5, that's 6. That's the different widths that I want to utilize. And if you count them, that's going to divide this into 5 equal segments. Okay. If you want to use right endpoints, what you do is starting with your very first segment between 1 and 2, you're going to utilize the right-hand side. So in this case, that's going to be the 2. You're going to go up to the curve, and then you're going to make a rectangle. You're going to do the same thing for the next one. You're going to go to the right, go up, make a rectangle, go up, make a rectangle, up, make a rectangle, up, make a rectangle. Are we okay with it? So my question then for you is, if my base is going to be the same, are my heights going to be the same? Just looking at this, the answer should be no, right? Like, there's no way that the heights are going to be the same. But I mean, I'm looking at them, they're all different. But how do you figure out the heights? Exactly. So you got to plug in, for example, once you know, like, for example, this very first height I got to do is f of 2. And then f of 3, f of 4, f of 5, and f of 6. Are we okay with it? So to figure out my height, I'm going to say it's going to be f of, I'm going to call it my base. I'm going to call this base, by the way. I'm going to call this change in x. Okay. So it's going to be my change in x times I. I'll explain to you what that means here in just a second. Cool? All right. So we're going to do this because this is just 5 rectangles. We can do this very quickly by hand. We don't need no formulas for this. So we're going to say the area is approximately, okay, so the first rectangle is going to have a base of 1 and a height of f of 2. And then the second one's going to be base of 1 and a height of f of 3, base of 1, height of f of 4, base of 1, height of f of 5, and then base of 1, height of f of 6. Are we okay with what happened thus far? Cool. So then the area is going to be, look, they all have a 1 in common. So you can technically pull out a 1, and then you can have f of 2 plus f of 3 plus f of 4 plus f of 5 plus f of 6. I picked this example just to show you things. Personally, I would not write any of these things down that I'm writing. I personally jump straight. I do not write the first statement. I jump straight to the second statement. The base is always going to be the same, so you can always just have that on the outside, and then you're just going to have all your heights added together. Okay? All right, so let's go ahead and figure this out. So it's going to be a 1 is really not going to matter for us. So for time purpose, I'm just going to use my calculator to speed this up. Okay? So I have what? 2x squared plus 3. Okay? So if I plug in 2 into there, I get 11. If I plug in 3 into there, I get 21. If I plug in 4 into that one, I get 35. If I plug in 5 into it, I get 53. And then if I plug in 6, I get 75. Okay, so we got 11, 21, 35, 53, and 75. So now all you got to do is add all those values together. So we got 11 plus 21 plus 35 plus 53 plus 75. So we got that the area is approximately 195. Now again, I'm just using the calculator right now so that I don't make this video very long. Okay? You would be expected to do this one by hand. Question for you. Looking at this image and looking at this area, is that more or less than the actual area? It's going to be more. Okay? So here's my advice. Anytime you have a function that's increasing and you're using the right endpoints, it's always going to be more. But if you had decreasing, it's going to be less. Okay? Does that make sense? Because think about it. If you're increasing and you're going to the right-hand side, you're always going to pick the higher value, which means you're going to be over. But if you're decreasing, you're going to pick the lower value, which is the other vocabulary word that you ran into on section 2, I think, or 3, the lower sum. In this case, this happens to be the upper sum because you're above the curve. Questions about what just happened? Okay. What if I want to do a left endpoint? All right, is the width going to change? No. So I'm going to go ahead and skip to that step. I'm going to have the width, and I'm just going to have all my heights added together. So if I go back to this diagram, instead of starting from the right hand side, I'm going to start from the left hand side. So at 1, I'm going to go up to the curve, and I'm going to go a little bit below, and I'm going to be below, I'm going to be below, I'm going to be below, and I'm going to be below. It's a little hard to see, but it's basically here in the green. I don't even know if you guys can see green in your screen, but I think you can. As you can see, they are going to be below, so in this case we are going to be a lower sum. So if we're starting on the left hand side, that means that my first height is going to be f of 1, and then 2, 3, 4, and 5. So we're going to have f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 5, and that would get you your 5 rectangles that you need. And once again, so let's see, I'm going to do minus 75. So area is going to be approximately, if I plug in 1, guys, I'm going to get what? So what's 5 plus 11 plus 21 plus 35 plus 53. I'm going to have pretty much the exact same values for all of this. I'm not going to have the 75 this time because that was my last term. That gets replaced with this 5 right here. So if I do that, that means that the area, it's approximately, according to this, 125 if I add all of these numbers together. Okay? And we can say then that the area for this case is going to be an underestimation, or it's going to be less than it actually is. So we can for certainly say that the exact area is going to be between 125 and 195. Are we okay with what's happened so far? All right. We can do the same problem, but this time we can do the problem using what we call the midpoints. So the way that the midpoint works is you're still going to have the same width. So in this case, we're going to have 5. So I'm going to just redraw this a little bit. So we had this idea here. We had this at 1, 2, 3, 4, 5, 6. So this right here is 6. Okay, so there's the area that I'm interested in. With the midpoint, okay, so my base is still going to be 6 minus 1 over 5, which is 1. But the height, here's what you do. We know that from here to here, like at 2, that's going to be a width of 1, right? What you do is you have to, on your own, figure out the middle point in between those two. So the middle point in between those two is going to be 1/2. So at 1/2, you're going to go up to the curve, and you're going to draw your rectangle using that middle point. So then the next one's going to be between 2 and 3, so it's going to be about right there. And then it's going to look like this. And then the next one's about here. And the next one's about right there. And then the next one is about right there. So as you can see, it's a little hard to see, but you have a little bit extra on the outside for all of them. We okay? And that's what the midpoint is. It's still rectangles though. So the area of a rectangle is still base times height. So we know then that the area is approximately, we have our base is still going to be 1 for all of them, but our heights are going to be different. So think about it. The height for the very first one is going to be f of 1/2. And then after that, if you know that the width is 1, you just keep adding 1. So then the next one's going to be f of 3/2, f of 5/2, f of 7/2, and then f of 9/2. So that's going to be 1, 2, 3, 4, our 5 rectangles. Okay, once again, we're getting lucky that on this example the width is 1, so I don't really have to worry about it. So I'm going to use my calculator once again just to help me out with this to speed the process. So we had 2x to the 3rd plus 3, right? I think that's what we had. No, 2x squared, I'm sorry. Plus 3, let me double check. Yeah, so that's what we have. I'm just going to use the table to help me out. So at 1/2, I'm at 3.5. At 1.5, I'm at 7.5. At 2.5, I'm at 15.5. At 3.5, I'm going to be at 27.5. And then at 4.5, I'm at 43.5. Cool. So there's my values. Once again, you can do this by hand. So let's see what we got. So we got 3.5 plus 7.5 plus 15.5 plus 27.5 plus 43.5 is going to be equal to 97.5. So our area is approximately 97.5 using the midpoints. Questions about that part? Yes.
Well, didn't it say to like only have 5 rectangles? Like how do you know how many trapezoids to make?
So this wasn't trapezoids, this was rectangles. How do I know what? I'm sorry?
I don't know how many rectangles to make.
Oh, you have to be told on the like at the beginning of the problem. So at the beginning of the problem, I personally just said let's do 5 rectangles.
Why did you draw 6?
It looks like 6, but I was just showing you where the midpoint is.
Oh, okay.
Sorry. So here's 1. Yeah, here's 2. Here's 3. Here's 4, and then here's 5. Yeah, I was just trying to show you where the midpoint came through.
Okay,
Cool. All right. Any questions about the midpoint, guys? What did I do? What? I'm sorry? 1/2? And yes, that's where I messed up. Good catch. Now, I noticed this, and I was kind of waiting actually to see if anybody said anything. Did you guys notice that this value was low compared to the other two? Yeah. What mistake did, I mean, it wasn't a mistake on the process. There was a mistake that I made where?
When it comes to width, you have to make sure you add the first point, right?
Yeah, we were not starting at 0, right? So yeah, our width was 1, right? And then our midpoint was in the middle of those two, right? But I wasn't starting at 0. I was starting at 1. So this could be a quick fix. Let's kind of scratch this. Thank you for catching that. Okay, f of 1/2 is impossible for me to use, right? Because it's not even on my interval. But I am going to use f of 3/2. Agreed? And then f of 5/2, and then f of 7/2, and f of 9/2. What's the last one that I need to use? 11/2. So that's going to be the difference. Cool. And that should be a closer value to what we had. So let me go ahead and fix this real quick. So I'm going to take, let me find out what f of 11/2 is. So 11/, that's 63.5. So, okay. All right, so I fixed it. Sorry about that, and good catch. It's approximately 157.5. And that falls more within the range that we had originally. Originally, we had a range from what, 120 to what? Yeah, 125 and 195. This makes sense. Our value should be somewhere in between because you can see that the gaps that are missing is a little bit less than what we had earlier. Are we good? Good catch, by the way. All right, so those are midpoints. What about trapezoids? Okay. With trapezoids, it's actually a little easier in my opinion, personally. Okay, so I'm just going to, once again, I'm just going to do a little rough sketch of what we got going on. So if this is 1, 2, 3, 4, 5, 6, that's what I'm interested on, right? So this is 1, and that's 6. So once again, I'm going to use 5, but in this case, I'm going to use 5 trapezoids of equal width. So what you do is you basically the same thing. To find your width, so you're changing x, we're going to do 6 minus 1 divided by 5, which is just going to be equal to 1. So this time what you do, this is a lot easier. Every 1 unit, so after 1, I'm going to go to 2. I'm just going to go up to the curve, up to the curve, up to the curve, up to the curve. Now it's going to be hard to see because of the way I drew this, but what you do is you basically, you want to connect those two lines. Like for example, you're going to connect the vertical line at 1 and the vertical line at 2 with a diagonal line that makes a little trapezoid. And then you've got a little trapezoid here, a little trapezoid there, a little trapezoid there, and then a little trapezoid there. As you can see, if we had the power of zooming in and I was using like some kind of software, there's still going to be little gaps, but they're going to be smaller than anything else we've used. Now here's my question to you. What you've technically done, if I enlarge this, is you have trapezoids that look kind of like this. That's what you got going on. You got 5 trapezoids that look very similar to that. How do you find the area of a trapezoid? Okay, so you basically have 2 bases. So we're going to call this base 1, we're going to call that base 2, and then they call this height for a trapezoid. Height is what connects the bases. So the area of a trapezoid is going to be base 1 plus base 2 over 2 times height. Okay, now this is where you got to be careful. What you call height on a trapezoid, we're going to call what in our examples? Width. Your width. So when I come up with this equation, it's going to be the area is going to be equal to something plus something over 2 times your delta x, or your width. What is representing your bases? The height. And that's where sometimes some students get confused, the actual heights. So I'm going to call it f of x of I plus f of x of I plus 1. It's a little tough to see, but it's the next one. Okay, I don't really want to come up with an expression per se, it's just for example. So we call this one I, then the next one will be I plus 1, and the next one will be I plus 2, and so on. So for our example, here's what I want you to notice. First of all of these trapezoids, what are they going to have in common? They're going to have in common that in order for you to add them, they're all going to be divided by 2, and they're all going to have the same width. So that means that I can pull out a delta x over 2 from all of them, right? Now, here's what I want you to notice. If you look at the first trapezoid, so I'm going to call this trapezoid 1 and trapezoid 2. What do they have in common? They're going to share one of the heights. So here's what I suggest. So here's a little trick. So for the first trapezoid, all you got to do is f of your very first value, which in this case is 1. Cool? Plus, the second base is going to be f of 2, right? 2, 3, 4, 5. But you notice how the other trapezoid is also going to have the same base, so you're going to go ahead and say plus 2 f of 2's. And then that's going to be true for between trapezoid 2 and trapezoid 3. They're going to share this base. Between trapezoid 3 and 4, they're going to share this base. And then between trapezoid 4 and 5, they're going to share this base. So what I'm going to do is I'm going to do plus 2 f of 2's plus 2 f of 3's plus 2 f of 4's plus 2 f of 5's. And that's going to take me all the way to this shared height. And then the last one, does this one get shared? And the answer to that would be no. It doesn't get shared between 2 trapezoids, so you're only going to have 1. So the trick for this is the endpoints are always going to be 1. Everything in the middle is going to have 2 of them. Okay? So for this, the area is going to be approximately, okay, our width is 1, so divided by 2 is 1/2. And then now, again, I'm going to just use the calculator to help me through this process real quick. We have 2x squared plus 3. So I'm going to go to the table. If I plug in 1, I get 5. If I plug in 2, I get 11. So 2 times 11. If I plug in 3, I get 21. So 2 times 21. If I plug in 4, I get 35. If I plug in 5, I get 53. And then if I plug in 6, I get 75. And once again, just for speed purposes, I'm using the calculator. If I give you this, I'll probably give you less trapezoids so you can kind of speed up the process. Okay, so area is approximately 1/2 times. All right, so what we got? Go ahead and use the calculator for that. So we got 5 plus 2 times 11 plus 2 times 21 plus 2 times 35 plus 2 times 53 plus 75. So that's going to be 320, which means it's approximately 160. Does that value sound about right based on what we did earlier? Yes, right? I mean, it's between 125 and 175, so we're definitely getting closer to it, right? So it's a pretty good approximation, okay? All right, let me pause for a moment. Questions or any questions at all between left point, right points, midpoints, or trapezoids?
Have you explained what I meant in the earlier formulas?
No, that's what's going to come next.
So on like the test, it's just like one, right? You don't have to have like specifically this.
Actually, on the test, yeah, I'm going to say find the area using right endpoints, or find the area using left endpoints, or trapezoids, or midpoints.
For the AP test, would you be choosing, or would it still tell you?
Same thing. On the AP exam, they're going to tell you what to use. So if they say area, you can use whatever you want. Okay? If they ask you find the exact area, you're obviously personally, you're not going to use anything you're doing today. Because none of this give you the exact area, right? But if they say find the approximation, they have to tell you what they want you to use. Otherwise, there's too many things you can do, and it's just going to make it difficult for them to grade. So that they will tell you what to use and how many rectangles or how many trapezoids.
Okay, thank you.
You're welcome. All right. The last thing we're going to talk about is, well, it's all nice that we can get approximations, but we're actually more interested on actually figuring out the exact area. Okay? So we're going to use the idea of rectangles to help us out. Okay? We can do this with trapezoids, but it just gets way more complicated. So let's go ahead and, again, I'm going to kind of sketch this out to kind of a rough sketch of what it was. So this was 1, 2, 3, 4, 5, I don't know, this is 6 right here. I want to know exactly what that area is. So here's the thing, I'm still going to use rectangle, so I know that area of a rectangle is going to be base times height. Cool? Now, here's my question. Earlier, we figured out that the base was basically taking the b value, subtracting the a value, and dividing that by how many rectangles we wanted. Agreed? Now, here's my question. In this case, you have f of x is equal to, what did I, was it 2x squared plus 3? Is that what I had? Yeah, 2x squared plus 3. In order for you to figure, and then, I'm sorry, from 1 to 6. So to figure out our width, we're going to say 6 minus 1 divided by the number of rectangles we want, which in this case is going to be n, because we don't know how many we want, okay? So we're going to say that this is 5 divided by n. Are we okay with that part? So then this area formula is going to improve, and instead of saying base times height, now it's going to say 5 over n multiplied by your height. Are we okay with that? Okay, let's go back and use numbers. So earlier we said we wanted 5, right? So that's how we came up with 1. How did we figure out the heights if we wanted to use right endpoints? So like if I was starting at 1 and I knew that my width was 1, how did I figure out what the right endpoint was? You plugged it into the function. Well, before you can plug into the function, you got to first figure out where you're at. So if you're starting at 1 and your width is 1, then you went to 2, and then you plug 2 into the function for the right endpoint, right? But how did you figure out that it was 2? It was based on your width and based on your starting point, right? So here's what you got to do to figure out your potential heights. I know that I'm starting at 1 in this case, right? To that 1, I need to add my width. Agreed? And that gets you the very first height. And then what did you do to figure out the next height? So like we got that one. And then what did you do to figure this one out? Well, you added another 1, right? So from here you added another 1, right? But now think this through. You added 1 from here, but if you go back to the beginning, you added 2. So that would be like saying 2 of those. Yes? If you wanted to figure out the third one, If you go back from the beginning, it would just be like adding 3, right? So it'll be 1 plus 5n. Okay. Have you guys noticed a pattern? If I wanted to find the fourth one, that would be 1 plus 5 over n to the 4th times 4, right? And so on. Okay. The reason why I'm writing it this way is because we want to come up with an expression in terms of I. So that's where the I comes in. You guys ready? Technically, this is multiplied by 1. Do you guys notice that all of this have the exact same thing with the difference of 1, 2, 3, and 4? So to figure out my height, what I'm going to do is, my height is going to be evaluated at f of this expression times I. So we know that all of them have a 1, all of them have a 5 over n, but they all have different numbers, 1, 2, 3, 4, 5, 6, 7, 8. You are going to represent those numbers with an I. Because if you plug in 1, you can get the first one. If you plug in 2, you can get the second one. If you plug in 3, you can get the third one, 4, and so on. Why am I using I? That is because on a previous video or lesson, you learned some summation formulas. And did you notice that all those summation formulas you learned, which by the way, I'll go ahead and write them down, they all started at 1, I equals 1. That is the reason why I'm starting with I here. Cool? So all the summation formulas, so if you had a constant, you learned that it was the constant times n. And then you had another summation formula for if you had just something linear, which is just I. That one is equal to n times n plus 1 divided by 2. And then you were introduced to a quadratic. So 1 to n of I squared, and that's n times n plus 1 times 2n plus 1 divided by 6. And then the last one you were introduced to was from 1 to n of I to the third power, and that one is equal to n squared times, I think it's n plus 1 squared divided by 4. Okay? We're going to use that information to help us out. So let's kind of recap. What I now found out is that to find the area of one rectangle, it is equal to the base, which is 5 over n, times the height, which is going to be f of 1 plus 5I over n. Is anyone lost as to what I've done so far? Are we okay? Alright, so here's the trick. You're going to be adding a whole bunch of rectangles, right? How many are you adding? An infinite amount. Can you add an infinite amount? No. So this is where the idea of calculus comes in, and it's going to help you by doing what? Yep. We're going to take the limit as n goes to infinity of the summation starting at 1 and going to n of this expression. Cool? Alright, now I want you to think this through. This is where some students get confused. You see how this says I right here at the bottom? That's the variable. So n is just going to be a constant. Okay? So here's what we got going on. We got the limit as n approaches infinity of, we got 5 over n. We need to figure out what this is equal to. So how can I figure out what f of 1 plus 5I over n is? Just plug it into the function, right? So if you have the function, remember the function was 2x squared plus 3. If you plug that in, that's going to be equal to 2 times I plus 5I over n squared plus 3. Cool? Alright, so let's keep going. So we got the limit as n goes to infinity, starting from 1 to n. I got this 5n, and then I've got this 2, and then I've got to actually expand this out. So 1 plus 5I over n squared, that's going to give us what? 1 times 1 is 1, plus 10I over n, plus 25I squared over n squared, plus 3. So now it's just a dreaded algebra, honestly, okay? Take your time, make sure that you double check everything, okay? We'll get there eventually, just have some patience. Have I lost anyone so far? Okay, so let me go ahead and tear this down so we can continue. Okay, so I've got to go ahead and multiply things out, and then I'm going to use some properties to help me make this process easier. So we've got still the limit from 1 to n. I still have this 5 over n. Now I'm going to multiply the 2 in. So 2 times 1 gives you a 2, right? But plus this 3, that's going to give me a 5, right? And then 2 times 10i, that's going to give me 20i over n plus 50i squared over n squared. We okay so far? Okay, so now we've got the limit as n approaches infinity of, I'm going to make my last distribution, so that's going to give me 5 times 5 gives me a 25 over n plus 100i over n plus 250i squared over n cubed. And I forgot, right? This would be an n squared right here. Are we okay so far? All right. So now let's remember. Remember how the summation I told you that the variable's I? That means that n is just a number, which means it's just a constant. So you learned some properties of summations, and you were told that if you just have a constant, you can just take it out of the summation. So what I'm going to do is I'm going to rewrite this, first of all, as 3 different summations, and then I'm going to pull out the constants. So the very first one is going to be 25 over n summation from 1 to n of 1 plus 100 over n squared summation from 1 to n of I plus 250 over n cubed summation from 1 to n of I squared. Does anyone need an explanation of what just happened? We're good? Right. So now what I'm going to do is I'm going to use formulas for what I have just boxed in here. I'm going to replace that with the formulas that I just mentioned earlier. So these were the formulas that I mentioned earlier, right? So that very first box right here, this red box, it's going to be the first one, which says if you just have a constant, you take that constant and you multiply it by n. So in this case, I'm going to have the limit as n approaches infinity of 25 over n multiplied by n. Are we okay with that? Plus 100 over n squared multiplied by, okay, the formula for I is going to be n times n plus 1 over 2. And then plus 250 over n cubed. And the formula for I squared is n times n plus 1 times 2n plus 1 all over 6. And if you notice, all of the sigma notations are gone. All of your summations are gone because they got replaced with summation formulas. And then this become very easy limit questions because you can split this up into several limits. This would be the limit as n approaches infinity of 25 for the first one. Cool? And then the second one would be plus the limit as n approaches infinity of this 100 and this 2, they can cancel out, and this can become 50 times n squared plus n over n squared. We're good so far? All right, plus. Now this is where I'm going to do a little bit of algebra, so stay with me. Okay. There's a 2 up here, and there's a 6 up here. So what that means is that I can make this a 3 and that into a 1. Agreed? Are we okay with that? So technically, I'm going to have a 250 up here. I'm going to have a 3n cubed at the bottom. Do we understand what happened? Here's the reason why I'm going to do that and why I'm not even really going to clean everything up. If I already got rid of this 2 right here, this is just n to the first power, right? And this would be like a 1/2. Do you guys understand that? I don't really care about that 1/2 though. What I do care is what happens when I multiply this, this, and that. Well, what happens is I'm going to get a cubic, some type of cubic. And then I'm going to have other things. But I don't care about those other things. Why do I not care about those things?
Because of, if it's the same power, then you can just do the 250 over the 3 different.
Very good. When you do a limit to infinity, all you care about is the highest power. So this is very simple then. What's the limit as n approaches infinity of 25? Well, that's just going to be 25. What's the limit as n approaches infinity of this expression right here? Well, it's just going to be 50. 50 divided by 1, right? And then the last one is going to be 250 divided by 3. Did I lose anyone? So then I get 75 plus 250 over 3. The 75 times 3, that's going to give me 225 over 3, so I can get a common denominator. So then 225 plus 250, that's going to give me 475 over 3, which is equal to, so let's see, 475 divided by 3 is equal to 158.33 repeating, and that's going to be your exact area. And as you can notice, that is indeed in between 125 and 175, which is what we originally found by using 5 rectangles of equal width. And then as we use the other sums, we get closer and closer. So in other words, out of the trapezoids, the midpoint, the right endpoint, and the left endpoint, which one was the closest one to the actual area? I think it was the trapezoids, wasn't it? Yeah, for the trapezoids, we got 160. That was the closest one. The trapezoid is the one that got us the closest to it. Cool? Alright guys, so this has already been a longer video than I expected it to be, but I think it was very useful in my opinion to really cover up a lot of points that you've been learning over the past few sections. So is there any other questions or any doubts that you have before, I let you guys go for the day?
So I was kind of confused on like the notation. So on like the, I think there was even some video you had like the limit of like two lines and then delta and then two lines. It's approaching like 0. That was like the same thing.
Yes. So here's what happens. There's 2 ways of doing this. The other way doesn't really get taught, or I don't teach it because it's too out there. So you were introduced to this idea. So it was, I think it was this, right? Delta, and then goes to 0 like that. Okay. This right here is called the norm. What that is, dude, is basically, you can do this one of 2 ways. You can do it the way we did it, which is basically make an infinite amount of rectangles that are the same width, right? Or you can do it this way, which is the opposite. You basically make your first rectangle the biggest, and then what happens is the widths, this right here means width. What it's basically doing is decreasing the width until it reaches 0. But what that would mean is that you would have to use rectangles of different widths, and it just makes the math more complicated, and it gets you to the exact same spot. So this gets you to the same idea of just doing this, which is what we did. And that's what I would like you to cover instead of doing the other way. Cool? You're welcome. What else, guys?
As of now, there's not much connection between the antiderivatives and finding area, right? Like,
No, that's what you're learning basically today. So that's why I said today's going to be like, if you guys stayed, it's just because you wanted a review. But on 5.4, you finally make the connection between an antiderivative and area. How are they connected and why are we talking about them right now? There has to be a connection, right? Why would we begin talking about antiderivatives and then all of a sudden switch it to area? So in 5.4, today you're going to learn what's called the fundamental theorem of calculus, and it shows you how the two are connected.
Okay.
Wait, so if we did the anti-differentiation of the function you gave us originally, would we get 158.3 or would we another?
Yeah, so what you're going to learn today, so I'll show you real quick. You're going to learn this today. So it might go a little bit over your head, hopefully not. But you learn, again, in section 3, that if you want to find the area, so this was between 1 and 5, right? Or was it 1 and 6? 1 and 6, right? 1 and 6, and then you had 2x squared plus 3 dx. If you use actual calculus, here's how it's going to look. So this is kind of like a preview of what you're going to learn today. Or if you stuck around, just like this is what you're going to learn, so you can just kind of stick with it, okay? And you don't have to watch the video. You're going to anti-differentiate like this right here. So if we anti-differentiate this, this will be at 1, so it'll be x to the third, and divide by 3, right? And then this one would be plus 3x, right? Here's the difference. When you have numbers here, you do not have to put a plus c. What you do instead is you put a vertical line, you put a 1 here, and then you put a 6 up there. This is all notation, and I'll explain to you what that means. I'm not going to talk about how and why this works. If you really want to know, then do watch the video. But if you just want to learn how to do it, then here's how you do it. You anti-differentiate, you make this vertical line, you put the 6 and then the 1. What you're going to do next is you're going to put the 6 inside of the function first. So you're going to do 2 times 6 to the third power divided by 3 plus 3 times 6. Okay? I'm going to put that in brackets. And then you're going to do the same thing with the 1, but you're going to subtract that. So it's going to be 2 times 1 to the third over 3 plus 3 times 1. Whatever the result of that is going to be the exact area. So let's just go ahead and do this. This shouldn't be too bad. Okay? So basically, what we have here, just to make my life easier, so what's 6 to the third power? That's what, 216, right? So that's going to be 216 times 2, that's going to give me 432, right? Plus 18. Minus, this is just going to be 2/3 plus 3, right? We okay? All right, so I'm just going to combine those two, and then see what happens. So we got 432/3 minus 2/3, that's going to be 430/3 plus 15, 18 minus 3, right? Now 15 in terms of thirds, that's going to be 430/3 plus 45/3, which gives us what? 475/3. And as you can see, that is what we got here earlier, 475/3. Which method do you like? The one that took 4 lines or the one that took an entire page? Let's hope.
We have to know both, right?
Not for the quiz. This is new. So this is what you're learning today. So this is not on the quiz for Monday. This is the shortcut. This is kind of like, remember when we're doing derivatives and then I had you do derivatives with limits and, you know, it kind of sucks? Same idea. I always like to make sure that you guys understand that everything we do, all the shortcuts, they work because there is a limit working on the background. Cool? All right, anything else, guys? Yeah, that was kind of magic, John. I just saw your message. Yeah, dude, it's so much easier. The fundamental theorem of calculus, amazing compared to doing all of this by hand. All right, so if you have any questions, let me go ahead and stop this video real quick.